Okay, Algebra 1 students, we're going to go ahead and get started with our new unit today. We're going to start into Unit 2, which is over functions. That will be a term that will follow us through this algebra year of Algebra 1 here. So, the first thing we want to do is start off with lesson 2.1 here, talking about functions and relations. So we'll get an idea of what those are. So first thing we need to define is what in fact is a relation. And a relation is simply going to be a set of ordered pairs and what this means is there is going to be an output for every valid input that we have. Okay. A lot of this will make sense as we go on further. We'll get these definitions in, and then we'll go about doing some practice and whatnot. So. Need you to recall about these ordered pairs. Remember that an ordered pair has an x and a y value, and it's arranged. I'm going to let you think on your own here for just a second which one comes first. Hopefully you recall that it is in that order x, y. Now a relation can be represented by any of these four methods, okay? And that's what we'll see throughout this lesson. One is a table. Two is an ordered pair, like what we talked about just earlier. The third one is a mapping diagram, and a mapping diagram will come in handy a little later on when we are trying to decide whether or not a relation is in fact a function. Okay? And the last one is a graph. So what I'm going to do here is I'm going to fill in these blanks and let you fill those in. You'll notice that these all involve the same pairs. These are ordered pairs here, -3, 2, -1, 0, 1, -2, and 1, 3. And you'll notice that we've got the same values throughout. Okay, we've got those four ordered pairs that we are dealing with. Need you to remember that when we go over to this graph, okay, so you may want to pause right now and get all this filled in. I'll give you a second to do that. Okay, now that you're back and have hit play, remember when you're graphing these points, the x value comes first. The x value moves horizontally. So when I graph this first point, I moved left 3, 1, 2, 3, and up 2, 1, 2. I moved left 1 and up or down 0. I moved right 1 and down 2 since it was negative, and I moved right 1 and up 3. Okay. Now this mapping diagram here is something that you may not have seen before. That essentially tells you where each input is going. So -3 went to a 2. -1 went to a 0, and we actually had an input of 1 go to two different locations, a -2 and a 3. Okay. So we'll move on here and get to know some other vocabulary. Domain and range. Domain is the set of inputs, or what we will commonly call the x coordinates of our ordered pairs. And along those same lines, the range is our set of outputs, or the y coordinates of the ordered pairs. So our input is what we have first. the direction we head first. Our output is where we move up and down, or vertically. Just to give you an idea on that. Now, if we take this example I have written down here in blue right here, if our relation is made up of these ordered pairs, all of these ordered pairs, which is what we dealt with up here, same values. My domain, then, is going to be all of my x values. So -3, -1, 1, and 1. However, one thing to keep in mind is when we are listing the domain and the range of a relation, we will not list a number more than once in the domain. So start with that -3, and then we had -1, and then 1 occurred twice, but we only write it down once for the domain. Now the range, when putting those in order, and we will typically put the domain and range in numerical order, not in the order in which they came. So to put the range in order, I've got a 2, a 0, a -2, and a 3. So I would write down that -2 first, followed by the 0, the 2, and then the 3. Okay. So we've got an example down here. I would like for you to identify both the domain and the range for these following relations. So if you would, just pause the video and do this on your own. Okay, now that you've come back, I would like to go through real quick the domain and the range. The domain for these in numerical order would be 0, 3, 4, 5, and 7. Again, those are all of my x values. And the range would be 0, 3, 5, and 6. And those were the y values. Now, if I look over here, I tried to graph these close to where they needed to be, so they would be pretty obvious what those values were. When I'm looking at these points, I can look at the domain. They are all of our x values. So I can start furthest to the left. That would be 1, 2, 3, -4. And work my way over. I've got a x value that's at -2. I've got an x value. I've actually got two x values that are at 0, right? But I only list that once, and I've got an x value that's at 1. Now the range, I'm looking at my y values, right? So I have a couple down here at -1. I have one up here at 1, and I have a couple up here at 2. So that would be my domain and range for those. Now we'll move on to another away from the domain and range of a relation, and we will move on to identifying what are functions in this case. Okay, so I'm going to check something here real quick. Alright, a function is going to be a special type of relation. Let's switch up colors here, get fancy. Special type of relation where each input is going to have, this is important, exactly, okay, each input will have exactly one output. Oops. Alright, to illustrate this, I want you to think about the domain being people or a person, and the range being a place. Okay, actually, I saw a good example of this in our lesson today that I had not used before. So what I want you to think about is the domain, or the x values being people, and the range or the y values being the place. So remember, or you don't have to remember, just think about a person. Can they be in more than one place at the same time? Can any one person be in more than one place at the same time? Well, no, they cannot. So a person can't be in more than one place at the same time. However, with certainty, more than one person can be in one place. Think about when you go to the mall. Or is there more than one person there? Obviously, yes. Okay. But you can't be at the mall and the grocery store all at the same time. Okay, so if you think about that, the input has exactly one output. So each person can only go to one place. Now, that does not work back and forth because, as we said here, more than one person could go to the same place. So this does not work backwards, and we'll kind of illustrate that here. Let's look at these right here, these three examples of mapping diagrams. And does each input value have exactly one output value? Does that just have one? Does that just have one? Yes, it does. So this right here would be a function. Okay. What about this one? Does each input value have exactly one output value? Well, right away we see that the 1 will go to 3 and go to 5. So no, this would not be a function. You can see, remember, think of this as a person. Can a person be in more than one place at the same time? If the answer is no, then it is not a function. And lastly, 1 went to 3, 2 to 5, 3 to 5, 7 to negative 1. That would be a function. And you might say, well, the 2 and the 3 both went to 5. That's okay. These are both different people, right? They went to the same place. That's possible. Okay? All right. Now, if we are given a set or a relation as a set of ordered pairs, it's often easier to use these mapping diagrams. Okay? These mapping diagrams to determine if it is in fact a function. Okay, got ourselves a key point here. I want you to really, because this will help you out. If a value in a domain repeats, so if one of my x values repeats, then that relation will not be a function. Okay? Will not be a function. So, with that being said, let's look real quick at these examples of tables. We've got all these x values corresponding with these y values. 1, 2, 2, 4, 3, 4, 4, 6. Do any of my domains repeat? No. Therefore, this would be a function. What about over here? Do any of my domain values repeat? Yes. I've got a number 1. Consider that to be the same person. Can that same person go to 2 and to 4 at the same time? No, they cannot. So this would not be a function. Okay. We'll move on to the vertical line tests. We won't take too long on this vertical line test, just because it's pretty visual. I'll just let you kind of follow through here. If you need to pause and slow down, feel free to do that. If any vertical line passes through 1 and only 1, if a vertical line passes through 1 and only 1 point on the graph, then the graph is a function. Okay. So looking at that the other way, if any vertical line passes through a graph 2 or more times, or at 2 or more points, then that graph is not a function. Okay, so this is really straightforward. If I can draw any vertical line, okay, if I can draw any vertical line through more than one point, then that particular graph is not a function. If it only goes through one point, okay, so let's take a look here. We'll go with red lines. So can I draw any vertical line through more than one point? That only went through one, that only went through one, this only went through one. Okay, so therefore use the vertical line test to determine if the graph is a function or not. Here we would say yes, that is in fact a function, right? Now let's look at the next one. Can I draw a vertical line anywhere on this graph that would go through more than one point? Well, I see a spot right here. Went through more than one point. Therefore, is that a function? The answer would be no. What about for this one? Do I even need to draw a vertical line anywhere? You know, your vertical line test can just be visual if you want it to be. So that appears to be a function. What about this one? Can I draw a vertical line that would go through more than one point? Yes, certainly. That goes through 2 points. Any vertical line that I draw within the range there will go through more than one point, therefore it would not be a function. And what about this funny shape here? We'll learn a little bit more about that later on. Obviously that is not a function either. Okay, and this line, can I draw any vertical line that would intersect that more than once? No, I cannot. So that would be a function. Now, just a little side note here. Are all lines functions then? Any line that I draw, can I draw a vertical line? So think about that to yourself for just a second. Even pause and think about any line that might be that might not be a function. Okay. Hopefully you thought about one particular case where a line would not be a function. And that particular case would be actually the one that we use as our test right here. A vertical line is not a function. Okay? That's the only line that's not a function, is a vertical line. Okay, we've just got 2 more slides to go through. We'll try to do those in a timely fashion and get this recording under 25 to 30 minutes. So, we're going to talk about the inverse right now. So the inverse of a relation. An inverse of a relation does, really simply just reverses the mapping process. Okay? So when we talk about the inverse of a relation, we're talking about reversing the mapping of the domain, or our x values, to the range, or our y values. Now, if that doesn't make sense, hopefully this quick little example I give you will make a lot more sense. And I'll just tell you, let's say I had an ordered pair that was AB. If that's an ordered pair in the relation, then there is a specific ordered pair that will occur in the inverse of that relation, and that specific ordered pair is simply this: B, A. All I do is swap them. Okay? So, hopefully that's pretty obvious now. So, we go to this quick, easy example here. We've got our relation here. We've got 4 ordered pairs. And I'd like for you to pause and go ahead and write in the inverse of that, what you think the inverse would be. Okay, hopefully you've filled that in. We would go 6, -3, 0, 4, -2, 0, and BA. Okay. We simply swap places with our x and y values. Now, the graph of a relation and its inverse are what we call reflections. Reflections. And they are reflections across a very specific line, and that is the line y equals x. Okay? Now, that line y equals x, just think about plugging in values. If you plug in 1 for x, what does y have to be? Well, it would have to be 1, so there would be a point at 1, 1. If you plug in 5, there would be a point at 5, 5. You plug in 10, there would be a point at 10, 10. So it is a line, and we'll draw this on here later, that goes up through the coordinate plane just like this. It goes through the origin and has a slope of 1. This is in the form y equals mx plus b, where m is 1 and b is not there, therefore b must be 0. Okay? Now here's our relation. What I'd like you to do is on this graph, push pause for a second and then plot the inverse points as well. I've got the relation plotted. I'd like for you to pause and plot the inverse points. Alright, hopefully you took care of that and you've got those 3 points plotted. I've already got this filled out, and I'm going to just click a button here and show you what I've done. Oh, I did forget to I forgot to fill in the points. I knew I was going to forget something there. I should put this in green as well. Give me just a second. So 3, -3, 0, -3, and 5, 4. So hopefully you graphed all those points okay. You were able just to flip them, just to flip the coordinates, and then graph those points. And what I did to show you this reflection, and now my scale is not perfect. My x values aren't the exact same as my y values, so it may look a little skewed, but it's pretty close. I connected these dots so you could see the shape that it drew. And then you can also see that this line y equals x, I want you to pretend that I've got a piece of paper right here, and I just folded that paper on that line, y equals x. By creating the inverse of this relation, I have essentially put the mirror image over here, if you can see that. Okay? Alright. And that was across the y equals x. That's what switching all of the values does for me. Alright? So I'd like for you on your own here to go down and hit pause and just take a minute or two and fill this in, if you would. Okay, now that you're back, I am going to fill that in. So if you'll notice, I simply switched all of my x and y values. I flip-flopped all of those. Okay, and if you need to slow down and pause and fill these dots in, you can. And I made them different colors. So the relation is in blue, I believe. Now if the relation is in blue, does it pass the vertical line test? Is there any vertical line that I can draw through there that would go through more than one of those points? And from what I can see, I don't believe that there is. So I would say that the blue one, the original relation, is in fact a function. However, what about the red? When I plotted the inverse, I see here that if I drew a vertical line down through right here, I would cross 2 points. So, are both of these functions? No, they are not. There is not a relationship between whether a relation is a function and its inverse has to be a function. Those will stand independent from one another. Alright. If you need to, hit pause and go back and review this real quick, but we will move on to the last page of our lesson today. And that is doing our equations. Okay, an inverse of an equation, because if I can graph a line, I also want to be able to graph its inverse. That will come in handy at certain particular instances. So to find this inverse of an equation, we simply interchange the x and y variables and then solve for y, because we like to have it in slope-intercept form, right? We won't always have to have it that way, but for right now, that's how we know how to graph a line. So we're going to find the inverse of this value right here, and here's how I will do that. A couple easy steps. Simply switch the x and the y. So now I've got x equals 2y plus 4. That was easy, right? So what would I do next? Well, in order to solve for y, I want to get y by itself. I move the 4. Okay? So if I move the 4, I'd have to subtract it, right? So I would have x minus 4, and that's going to equal 2y. Now what would I do next? I'd have to divide by 2, right? Divide everything by 2, and I'm going to flip-flop this, so these 2's are going to go away. I'm going to have y equals x minus 4 over 2. Now I want to write this in slope-intercept form. So instead of having this all over 2, I'm going to write it individually. I'd have y equals x over 2 minus 4 over 2, and now I can kind of simplify. Wait for this to stop here. Okay. So y equals x over 2. I don't really like it like that because I want it in mx form. So the m would be 1/2, right? That's 1 over 2. And then I'm multiplying that by x. So now my slope I can see is 1/2. And minus 4 over 2, which is 2. So that's how you would do that. You swap the variables and then solve for y. So I like for you guys to go down here and try to do that on your own. So hit pause and take just a few minutes and try these on your own. Okay, now that you are back, I am going to show these kind of quick. I won't waste too much time. So I'll rewrite these. X equals 2y minus 6, and I want to solve for y. Now I'm not going to show all of my steps. I will tell you what I'm going to do though. I'm going to add 6 to both sides. So x plus 6 will equal 2y. And then I'm going to divide both sides by 2. And I'm going to also write the y over here. So I'd have x, or y equals x plus 6 over 2. Divided both sides by 2 and just flip-flop them. Now I'm also going to rewrite this. Y would equal, that again is going to be 1/2 x, and the 6 over 2 would be 3. Okay. Over here, when I swap these, x equaled 3 minus 5y. Solve for y. I would add 3 to both sides, so I'd have x plus, actually, I would subtract 3 from both sides, right? So I'd have x minus 3 equaled negative 5y. And then I would divide both sides by negative 5. When I did that, I'm again going to put y over here, and I'd have x minus 3 over negative 5. And I need to think about that as being two separate problems. I've got x over negative 5, and I've got negative 5 over, or negative 3 over negative 5. So when I rewrite that, y should be equal to, that would be negative 1/5 x, right? And then I would have a positive 3 over 5, because negative 3 over negative 5 would be positive 3 over 5. The final one might have tricked you a little bit, but it's actually the easiest. Y equals 4, the inverse of that equation, I simply swap the x and the y. Well, there is no x, so my y would go to where my x is now. It's not there, so my y would no longer be there. My x would go to where my y is now, and I would simply have x equals 4. So y equals 4 is a horizontal line, if you remember, and x equals 4 would be a vertical line. Okay, and that's our lesson for today. Hopefully you got a lot out of that. Remember, you can go back, and the good thing about this is you're going to be able to pause the lesson and get a little bit more information. I did want to show you guys something really quick. Don't forget about our website. Okay, this SAS Curriculum Pathways, you can still go to it and get lots of videos. So don't forget that when you go to this, all you have to do is go in here and type in could 7 famous. Log in. Remember, always run something. There's nothing wrong with the stuff on here. You just have to tell it to run every once in a while. There's actually lots of good videos in this first 2.1 that may help you out if you're having trouble or difficulty. Another recommendation of mine is for you to, if you're ever worried or confused on something, don't be afraid to go to this website, Khan Academy, Khan Academy.org. They've actually got commercials on television now. I've been using this site pretty much since I started teaching. Use it here and there. But go there. You can search anything. For instance, I could search domain. Domain and range pops up. I can hit that topic, and it gives me a video right there. Domain and range, domain of a function. So anyway, I hope you're enjoying our new flipped classroom, and it'll give us a lot more time in class to do some fun activities and work on your quote-unquote traditional homework in class. Bye-bye.